多。
But I couldn't find a friend.
Like yeah. With the对，一种手势。你奇怪吗？
Okay, so let's start today's class. So today we will finish the synthetic control method, and then we will introduce another identification strategy called regression discontinuity design. So basically, we will finish all the important method for the causal inference. So I plan, not really sure, but maybe we will have 2 more in-person class. Then you will have the office hour and presentation. These might be go online. And also other extra lecture, maybe I will just record and the video and upload to the YouTube and you can watch. But the most important part, it's good, we almost finished. Okay. So any questions for this? Because I'm not sure whether the situation of COVID situation will become worse or not. It's possible it become worse, and I'm so maybe online course for the office hour or presentation maybe it's fine. Yeah, and in-person lecture actually is better, I think. But good things is we almost finished all the important part of this lecture, because we make our data tutorial and our tutorial will just become the video. And yeah, okay. So any questions?
So it's a presentation of the speaker. Because I saw there's a time slot for presentation order for Tzu-Ting. So does that mean have a presentation? May 11.
Now it's May 11. Yeah. But I will announce for this presentation and compulsory office hour to let you know what's the structure and the guideline for this. Yeah. Okay, so last time we have introduced the synthetic control method, and these methods are especially useful when you do not have a common trend. Your control groups, if you just do simple average for all the untreated units, sometimes it may not generate a common trend, has a common trend as the treated unit. So in that case, it's possible you can just use the weight average. Basically, you assign higher weight to the untreated unit who are more similar to the treated unit, and use this weighted average to construct so-called synthetic unit that can reproduce the outcome path before treatment occurs. So if you can find a way that can basically to generate the same outcome path before treatment happens, then you can compare the treated unit with this synthetic unit. The gap after the treatment happened can represent the causal effect. Okay. So this method, the goal is there's a treated unit 1 get the treatment. And we only can observe, we want to evaluate the treatment effect. And we can only observe treated unit 1's outcome if they receive the treatment. If this treated unit 1 receives the treatment. We never know it's Y0. So this Y0 is counterfactual. And the synthetic control method suggests we can use untreated units, the weight average of untreated units to construct this Y0 counterfactual. So basically, it's choose a weight. So each untreated unit will receive the weight. And the weight is amount to the 0 and 1. So some control units might receive 1 if they are very similar to the treated unit. So all the weight will just belong to this untreated unit. And we choose the weight to minimize the difference in the pretreatment characteristic X between the treated unit and non-treated unit. So basically, it's try to minimize the distance X, the treated unit 1 and other control unit by choosing this weight. So this distance function may have a lot of types. So it depends on the algorithm, it can have different distance function. But generally, we try to minimize this difference by choosing the weight. And the X include observed characteristics Z, like population size of other states or the share of the young people if you evaluate the effect of the anti-tobacco policy on the California cigarette consumption. And also, more importantly, is the pre-treatment outcome. So each year's pre-treatment outcome, we will try to match. And if we can find this weight, we will construct the synthetic control unit. And we can use this synthetic control unit's outcome compared with treated unit's outcome to get the causal effect. Okay. So we just compare the treated unit's real outcome with this counterfactual outcome constructed by the weight average of non-treated units. We can get a causal effect. Okay. So that's the review for the last lecture. So different weights will give you different synthetic units. Okay. So that means if you use different characteristics, you will get different weights and different causal effect. So sometimes we will try to know whether our result is sensitive to the choice of our pre-treatment characteristics, the observed characteristics. Yeah. Okay. So that's the last lecture. And in the last lecture, we also discussed how to do hypothesis testing when we use synthetic control methods. And since no one haven't derived the asymptotic theory for our synthetic control estimator, so we don't know what's the distribution of a synthetic control estimator. But instead, we use so-called permutation method for the statistical inference. So it's required we estimate a lot of placebo estimates. So basically, the first step is we use each unit in control group and apply synthetic control method to get a lot of placebo treatment effect. And we compare this placebo effect lab using other characteristics, other control groups, control units. So here I change the notation, I equal to 2 to j. So I correct this part. So compare each control units, the placebo effect with the real treated units synthetic control estimate. And we want to know how many, the share of the control units, its synthetic control effect is bigger than the real effect. The treated units, its synthetic control estimate. So if a lot of placebo effect are bigger than the real effect, that means our estimate for the treated units maybe is just by chance. It's not really represent the causal effect because we use randomly choose other control units, untreated units. It also produce very large treatment effect, but actually shouldn't. No treatment happen for them, but we still find a lot. That if such situation a lot, you will get very high p-value, and that means your causal effect is not significantly different from zero. But if your real effect is very large compared to other placebo effects, that means the p-value is very small. That means you might find the real effect. The causal effect is significant from here. Okay, so that's also the review for the last week. Yes, treatment group can in the control group. When we do placebo effects, placebo estimate. Yeah. So you do like this is the real effect. The California one is real. There's some policy happened in 1989. That's something we want to evaluate, and we get this effect. But we want to know whether these big effects is really represent the true effect or just by chance get this. So we run a lot of placebo effect. For example, we use Alabama and run the same synthetic control. And California also include that in this. Okay. And we find this is very small. And we do this for all the states. All states we do this. And we calculate how many these placebo effects are bigger than the real one. If there are many, that means this real one does not really represent the causal causality. If very small and the real effect sounds like an outlier, it might suggest there's something happened in 1989 that only affects the California. Okay, so that's the hypothesis testing. And we also discussed last time, sometimes the quality of pre-treatment match for placebo estimate maybe is not very good. For example, this line, these placebo effects, actually before treatment happened, they are not very similar to their synthetic units. So in that case, we might need to eliminate this type of placebo effect when we calculate the p-value. So, and the criteria are based on the root mean square predict error, RMSPE. So the formula for that is you calculate for each placebo untreated units, you calculate their outcome with their synthetic units, and you calculate their difference, and sum over the pre-treatment period. So period 1 to T0 means treatment before treatment happened. You calculate all the difference between these units with their synthetic units. And if this number is very big, that means the matching quality for this untreated unit is not very good because they are not very similar. So in that case, you might want to eliminate the placebo estimate with very large RMSP because we don't trust their synthetic control estimates. So we don't use this estimate, this control, the placebo estimate when we calculate the p-value here. So sometimes if we exclude such untreated units, placebo estimate, we might get this result. So in this result, we only use 29 untreated units, produce the 29 placebo estimate to calculate the p-value. So in that case, you will find our real estimate actually is very negative compared to other placebo estimates. If we exclude the bad matching. Okay. So for example, here the p-value is 0. So it's very different from significantly from 0. Okay. So we will also further, when we calculate p-value, we usually will use so-called standardized p-value. So instead of directly compare the placebo estimate with our treated units, the real estimate, real synthetic control estimate, we will divide their RMSP. We will consider their matching quality before treatment happens, the pre-treatment matching quality. So if the RMSP, the predict error before treatment happens, is too large, this number will become small, because that means we don't trust this estimate. And if their RMSP is very small, this means this will become bigger. We put more weight on this placebo estimate. So this is also the way when we calculate p-value by taking pre-treatment matching quality into account. So usually we will use this standardized p-value when we compute the p-value. Rather than directly use the p-value, we use standardized p-value by taking the matching quality into account. So any question for this? So I add something in this slide so you can read this slide. So I update the slide. Okay, so we also discussed the data example. So you know how to use scene and scene runner. But today I will also want to let you know how to display the effective graphs, how to draw the synthetic control estimates graph by yourself. You can use two ways to do that. One is use scene runners subcommand to do that. Another is you can write your own code. So I will also let you know how to do that. Your code to display this effect graph. Okay. So you can open the data. I can open this data. And we focus on this part. So we open the data set. And we run the scene runner. So again, we evaluate the effect of anti-tobacco policy on cigarette consumption in California. So we run this, and we match the outcome cigarette consumption and the predictor, the covariates is beer consumption and income and retail price, and also the pre-treatment outcomes. And after you run this, they will generate a file called result. And this can help you to draw the synthetic control estimates with graph. So you should put the keep this option to keep the result, to save the result. And that will the result file name is called results. Okay. So you can see. So it will generate a new file called the result. So that's all. So this is all our original data set. Original data set is just let you know the state, year, and outcome, and other predictor. Okay, that's the original data set. And we want to merge our original data set with the result file we just generated. It can help us to draw the graph. Okay, so let me open the result file. So that's the result file. So the result file will store several useful things that can help you to draw the graph and do further analysis, especially for hypothesis testing. For example, it generates each state, including treated unit and non-treated unit. It's pre-treatment RNSPE. So this is basically is the matching quality before treatment happened. So you can use this number, pre-treatment RMSPE, to eliminate the bad matching quality, the placebo estimate with the bad matching quality. And this is a post RMSPE. That means only evaluate the difference between the real units and the synthetic units, their difference. And it's generate also let you know the effect. That is the real units with synthetic units, their difference. It's the effect. Okay. And it has all the states. So including the treated units and also the non-treated units, control units. So this is, you can consider this effect is the placebo estimate, placebo effect. And you can use this file to draw the graph to show the real California effects and other placebo effects. Okay. So we will merge. So when we run this and we save this result, and then we use combine the merge our original data set with this result data set, and using the state and year, state ID and year, that one-to-one merge. And then we will have the new file we can save. It's called SCN result. Okay. And that data set is just combine these two. So you will see sorry. Do it again. So after you combine original data set and the result data set, you have all the information that can help you to draw the graph. Then you can use SceneRunners, its own command to display the effect graph. And it provides one command called single treatment graphs. So you just type this. And the first thing you need to do, this -1 means right before the treatment happened. And also you put some label, for example, from the -30, the time periods, this is y-axis, it's -30 to 30. So this can adjust depends on your outcomes by yourself. And also affects maximum, the highest effect is 35. and minima is minus 35. So after you do this, you will generate the result like here. Okay, and the solid line is the real California effect, and other not very obvious, but there are some line here. You see, there's some line here. It's a placebo estimate. Placebo estimate. So that's something you will generate. But sometimes maybe you want to eliminate some pre-treatment quality is not very, matching quality is not good. So the pre-IMSP, the pre-treatment IMSP is too big. You want to only keep the pre-treatment IMSP smaller than some threshold. So usually we will use the treated units pre-treatment IMSP as a benchmark, and we eliminate like 5 times. If the placebo estimate pre-treatment IMSP is 5 times than the treated units pre-treatment IMSP, we will just eliminate them. So we only keep the pre-treatment IMSP smaller than 5 times of the treated units pre-treatment IMSP. Okay, so that's something you will need using the result file you just saved. Okay, so if you exclude them and do the same, type the same command, single treatment graph, you will generate a new graph that less noise. So some placebo estimate with bad matching quality disappear here, if you can see. Okay, so that's something you can manipulate to change. Okay, and also you can just type effects graphs. It will give you this graph. Just display the treatment effect for the treated units only, just one. If you don't want to see the placebo effect, okay, you can also do it by yourself, for you. But you can also use your code to generate the same things, not rely on this scene runner's code. For example, you can do that. But again, you need to first run the scene runner and save the result. You save the result. And after you save the result, your data will look like this. I just open. You have original data set, but you merge 2 data sets. You merge original data set and the scene runner's result file. So you will get the pre-IMSP, post-IMSP, and effects, this result. And you can use this result to draw the graph that I just showed you, but by using your own code. So you can just use the two-way, graph two-way. You might learn in the video. Because your homework too, you need to use this command to draw some graph. So you can watch it. But here I just let you know how to do that. So you will have a lot of placebo estimates. So one thing you can do is you just type every command, try to draw the placebo estimate for each placebo estimate. But you can also use the loop to draw this line. So, but I haven't discussed in the video. In the data, the loop is for value I equal to 4 to 29. This is the state ID. So you want to draw the graph, draw the line graph, effects and year. Effect is the variable you just generate, is the real unit and the synthetic unit, their difference. That's the treatment effect. And here is your horizon axis. And you want to draw this line. And for each state, you want to draw such line. And you can use this loop to help you to generate this very quickly. But you can also do this for each type from 4 to 39. Also, you can also do that rather than using a loop. If you think it's too complicated using that, but you can do that, and then you graph two-way, and the figure is you just store before, and also put other line for state 1, state 2, and state 3. State 3 is the California. So here we use a different notion to represent. Use connect line to represent. Others just line, typical line. And then you can also customize your graph. If you can draw your own, use your own code to draw the graph, you can also customize by typing the, for example, X title and the Y title. And the products will look like this. You can draw, this is emphasize, this is the treatment effect, and others just placebo effect. So maybe these will be better than you just use their comment to generate the graph. The graph generated by their comment. Maybe you can use your own code to generate it. And here I give you one example. Okay. So any questions? Because original command you cannot adjust this, but here you can adjust this by yourself here by changing here. And how to change this, I have discussed in the video. You can watch. Okay. So any questions? Okay. Okay. So we have finished the example, and today I would like to let you know how to, so far we just discussed the one treated unit. So the number of treated units, just one, and others are untreated units. And today we extend this framework to multiple treated units. And we want to estimate the average causal effect for these multiple treated units. Okay. That means the treated units, the number of treated units are more than 2. Okay. So if we have multiple treated units, the procedure of synthetic control estimation is the following. It's not very hard, but it's a bit complicated. The first step is you run the synthetic control estimation for each treated unit. So for example, now, not just California get the treatment, maybe Pennsylvania also get a treatment. So you first run the synthetic control for the California, and you get the synthetic California, and then you run again for the Pennsylvania, and you get synthetic control, synthetic Pennsylvania. And after you do that, you will get, for each treated unit, you will get the synthetic control estimate. For example, alpha I for each period after treatment happened. So for California, you get 1. And for Pennsylvania, you also get another 1. And you just sum over all the treated units. So G is the number of treated units. And you will get the average effect for these 2 treatment units, treated units. So just very simple. Originally you just have 1, so you directly use this alpha to represent the treatment effect. But here you just have G. The number of treated units is G. So you sum over all the treated units in synthetic control estimate, and you will get average treatment effect for each period after treatment happened. Okay. So this effect is average treatment effect. Okay. Average over the California and Pennsylvania, for example. Okay. So sometimes we want to do this, and So the next question is, we can get the point estimate for the average treatment effect by doing that. And the next question is, this estimate is significantly different from 0 or not. So we do hypothesis testing. And the hypothesis testing is again using the permutation method. But here it will be a bit complicated. Okay. So suppose Pennsylvania and California passed anti-tobacco law in 1988 and 1987. Okay, so you have two treated units. So first, you calculate the average treatment effect for these treated units by using the same procedure I just mentioned. You run the synthetic control for the Pennsylvania, can get some alpha 1. Another, you run synthetic control estimate for California, you get alpha 2. And how does the average is just take sum over and divide by the number of the treated units. You will get average effect, alpha bar. Okay. And we want to know whether this alpha bar is different from significantly different from 0 or not. So we need to do the permutation estimate. So this is how to estimate alpha bar. Is you run the synthetic control for California and for the Pennsylvania and calculate each periods their average gap. Okay. And Pennsylvania actually do not pass any anti-tobacco law in 1987, but we just give an example. Okay. And the step 2 is we want to do the hypothesis testing. So we need to generate the placebo effects. But now we have 2 treated units. So for each treated unit, we need to generate the placebo effects for them, for each of these 2 states. So the first we will do is, the first placebo estimate is for Pennsylvania. And the second one is for California. So for example, we do the placebo estimate. The first placebo estimate, you need to do two times. One is for Pennsylvania, one is for California. So for example, the first placebo estimate, the alpha bar PL1, you choose Alabama. This is for Pennsylvania, and you get the synthetic control estimate. And for the California, you use Alaska. So after you do this, you can calculate, you have 2 placebo estimates, you calculate average. And that's the first placebo estimate for this average effect. And then you pick another state and run again the placebo estimate. And first time you pick the placebo estimate for the Pennsylvania. And second is another state for the California. And you calculate again the average placebo effect to the second average placebo effect. Okay. And how many combinations you have is, in this example, we have 37 control units, control state. So for the Pennsylvania, you have 37 states can calculate placebo effect for their synthetic control estimate. And for California, you also have 37 states for California. But so for each realized placebo average effect, you use these 37. And how many combination is 37 times 37? So you will have 1,300 combination, possible average placebo effect. And you will compare this 1,300 possible average placebo effect with the real average effect to calculate the p-value. Okay. So very similar. You compute all the possibility of average placebo effects, and compare each of them with the real average effect for the California and Pennsylvania, and calculate the share of the placebo effect that bigger than the real effect within this 1,300. And if a lot of them are bigger than the real average effect, you will get a very high p-value, and that means your average effect you get is not really represent causal. It could be just by chance, because it's not always bigger than the placebo effect. But if you always find your real effect bigger than the placebo effect, that means this p-value is very small. You can safely say, maybe I got the significant result. Okay. So any question for this? So just a bit complicated if you need to run a lot of combination, because there are a lot of combination for this average effect. Okay. Okay, so here just extend to the G. If your number of the treated units is G, and very similar, and J is the number of non-treated units. And first things is you just calculate the average effect for these G units. So here, previous we just used the example just 2. And here just extend to G. So it's very similar. And then you calculate the possible placebo effect for all the average placebo estimates. And how many you have is the number of the non-treated units JG, and times G times. So you have JG power G, possible placebo effects. So suppose the number is NL, and then you can calculate the p-value by doing that. Okay. So you can, but if you understand the number of treated units just 2, this example, I think you can understand the more general formula. Okay, and you can do that using the theta. So for the multiple treated units, but you need to define one more thing is you need to define this new variable is a binary variable which is equal to 1, means the treated units in the treated period during the post-treatment period, and 0 means otherwise. So you need to define the new variable putting in this option D, within the D. So here I give you the example. So again, the treated units Pennsylvania and California. So you need to generate a new variable called D or other, depends on, so this can any name. And this binary variable will indicate the treated units during the post-treatment period. So for California, is the state ID is 3, and after 1989, they get a treatment. So this is D is equal to this, or Pennsylvania after 1988. So you just generate this dummy variable to indicate the treated units they are in the post-treatment period. So if you have 3 treated units, you just put more. And they might also happen in different timing. You just change the time. Okay. So if you define this, then you can run the thin runner, and outcome and predictor. And the difference is you put put the binary variable just generate in this D function, and it will help you to calculate the treatment effects and calculate the p-value. So yeah, so you can try. Okay. I also put the code here in the here data. Oh, for the multiple treated case. Okay. So you can run by yourself. And finally, I would like to remind you some practical issue when you use synthetic control method. One thing is computation time. Actually, if your treated units are too many, or non-treated unit number of non-treated units are too many, it will use a lot of time to compute, because you can imagine for each non-treated units you need to assign the weight to them, and the combination of the weights have a lot of combination if you have a lot of untreated units. And also sometimes you have a lot of treated units. It also will make you have more combination for the weight. So at least so far, the synthetic control, the sample size for synthetic control methods is seldom more than like 1,000. You cannot use very big sample. So usually we use synthetic control only for evaluate some using the country level data set or state level data set or city level data set. It haven't extend to the firm level or individual level, but potentially you can do that. But just computation time does not allow you do that. Okay. So one way you might be able to reduce the computation time is you just use the non-treated units that are more similar to treated units. So you can do some pre-selection by drawing the graph. Try to just use the non-treated units. Its outcome paths, its outcome strengths are more similar to the treated units, and you can just use these non-treated units because they should be assigned get more weight. So you just use this group of non-treated unit as your pool to generate the weight. That's one thing you can do. Another is when you do the hypothesis testing, now we still use the permutation method. And if you have very large, more than one treated units, you need to do try to produce a lot of placebo estimates. So for example, the example we just let you know is just 2 treated units. But the possible combination of the placebo effects is 1,300. So if you extend to 3, 4, 5, the number of placebo estimates you need to generate is a lot. And that will also take a lot of computation time. Yeah, that's something still we need to overcome. For example, some statistician trying to derive the asymptotic theory for the synthetic control estimator. So if they can derive this, we can just use this distribution rather than use the permutation method. Okay. And another issue is the synthetic control theory suggests pre-treatment periods must be longer enough related to the scale of the transitory shocks. So that means we need to have sufficient long pre-treatment periods to get the reliable synthetic control estimates. But this is ambiguous. It's unclear how long is long. There's no guideline for this, and or how to test this condition is hold or not. We haven't know this have this knowledge so far. Okay, so that's all for the synthetic control methods. And this is a new method, so actually the most harmless textbook does not cover this. But this new textbook, causal inference mixed type, the chapter 10 cover this. So you can read this. Or you can read Abadi's its review paper. They also let you know the guideline for implement the synthetic control methods. Okay. So any questions? If not, that's we can have the break, and then we will go to the regression discontinuity design.
这个方法第二个好，就是说它不需要一个 common trend。
对。
可是我感觉上新的 pre-treatment 的 period 你还是要有 pre-treatment 的 period 够长，以至于你才可以 match 它 data。
对，它要够，但是
这个 pre-treatment 本身就是一个 common trend 啊，它还是有同步啊。
没有，它那个 pre-treatment 如果对于 control group。它的简单平均可以很不像 treatment group 没关系，就是像一开始那个加州的例子，它可以，它很长，但它的简单平均可以完全不像它，就是没有 common trend。
简单平均可以不像它。
对，就是一般 different 的时候，它只是把所有没有得到 treatment 的州都拿来平均。那它如果这样平均的话，它其实会跟加州会很不像，就没有 common trend，所以它就做不下去。但是synthetic control 它只是进一步的去找到那个更像加州的，给它高一点的位置。去做，对。
但是他们都是要同步，就是说，我的同步是说，从1970到1988，他们同时这段时间都是有 data，
对，都是要 data。但是
第二天也需要，然后是现在的 control 也是需要，
对，
都是这一段时间，只是说，
对，
是在 control 它不需要说，你可以随时用它某一个州的某一个来取得它的不一定要查每一个州，所以说我说在 data 它假设有些它不是1970到1988这个时间，它可能有10年的资料。
中间有些没资料。
对，这样子
对，要么他就不要把它摆进这个那个破里。对。它等于资料缺失，
所以它就是要
对，都有资料，都要 balance， 然后要够长，对，确实要够长。
上一段可以随时找，你可以找其他。州的
某几年，他像我在刚 Stata 例子里面，他其实没有 match 每一年的，他只 match 某几年。可是就是 match 的时候可以不用每一年都 match， 可是你还是要有所有年度的资料，因为它只是用那几年的去产生那个位置，可是它产生完那个位置 apply 到算出这个 synthetic， 它还是要用到全部的资料。
就是关于这个我的资料，目前是就是它只有2000年到2019年的 Y， 然后我的 X 就只有2条，目前就只有找到人口跟那个 个median income 这样子。
对，我有问我学生，他有给我可能比较方便一点，但他美国的那个资料没有像台湾那么方便，可以有一个报表这样，但是有一个还算有系统的网站，你可以去下载州的层级的资讯。对，
帮我生成这个 Excel 好久。
对，我再寄给你。那但是你要看的那个大麻那个政策，它会发生在哪个时间？
对，它每个州都不一样，
对，
另外再查都没有关系。
对，应该说你要注意，就是你的实际这个 pre-treatment 的 period 要够长，你可能要10几，最好有10几年，所以你最好发生晚一点的。
比如说像第一个合法的 Colorado， 它是在2004年，然后我最多是要到2019到2000年，那我需要后面再拉长一点吗？
你如果有办法拉长，
可以，就是 Y 可以，可是 X 的话，就是因为还要去找那个超级麻烦。Y
可以是蛮重要 ，Y 就也你看能不能尽量能长就多长。
好，我尽量。
那 Y 是一定要有每一年的资料。
我知道 X 可以，
但 X 可以不用 ，X 不用 ，X 你可以某一个横断面，比如说你只有2000年的人口
，OK，
1995年的某种另外一个资料就可以，就是你就只是挑年度去 match。
Y 一定都要完整。
Y 要完整
的，
对。
那尽量长就尽量长，会比较好。
其实应该是说看你关心的那个 treatment 发生在哪个时点，比如说你发生在2014年。
2004对。
比如说我说2014年，然后你有2000年到2014的 pre-treatment period， 对，我觉得也算长了。
OK，
14年，然后你看就是14年这个实施之后到19年，就是你的 post 可以不用太长，就5、6年其实再长我也不太相信那个结果，因为再长那个后面不知道发生什么事。
好，了解。
其实也不一定很可惜。对。
外面买那个要买的，一般是先买颗的，有很多种卖的。
Every time I will record a video, but I just record the screen, so the quality may not be as good as in person.
But I can always follow my screen and then if I have questions,
Yeah, or we can have the office hour, online office hours also okay. And also, actually we try to prepare for the change for online. I guess maybe we will have in-person class or 1 or 2 class. 2 weeks.
two of my classes have already been switched.
Yeah, so but I almost cover all the important methods. Yeah, RD also is the last one. Actually, the last one is instrumental variable, but instrumental variable it's not really popular now. It's become a bit old-fashioned.
How do you choose the right type?
Yeah. So it's possible for instrumental variable will just have video. So I just plan at most 2 in person. Yeah. Or maybe next week we will change.
I'll
Yeah. And at least, and also later we have more office hour and presentation. So actually, it's also good timing just become a full-on. So all of your class except this is become online.
And macro, because I'm not too sure what's going to be the big data we have to offer, because like I've been having a little conversations. The next one is canceled. So yeah, cancel. So 2 canceled, 2 are still.
Yeah. So yeah, we prepare for online course.
But I think maybe macro as well, because it's a big class. It's everyone.
Professor Tong. Oh, okay. Yeah.
It's a small class, it's only like 10 of us, but hers is moved online. I don't know why. There's big data, the big class, so probably, but it's a big lecture course. Yeah, we're all waiting to hear.
Yeah.
你说比假设你加就是因为他那个就是你就是要传真音的对。
哦，没有，是因为那个你那个是文字，文字不可以转成数字，不是因为中文的问题。是文字就会用红色代表，数字是蓝色或黑色，他们两个是不一样的态度，你要让他们两个一样的态度，才可以做这样的转换。
所以我要先把文字转换成
数字，我觉得你不如把变成数字化比较简单。对，应该是吧？还是说我看一下你那个变数，我觉得你那变数可能只是 label， 它是蓝色的，蓝色其实是一个数字。
它其实是个数字。
对，它根本不是文字。你可以看，你可以这样点它就知道它是对，知道。蓝色的文字其实是背后数字，它只是蓝色 label 什么文字。那红色是真的是文字。所以你那边其实就是2变0。
好，了解。
哎呀。
你们有多少课是已经变线上的？
目前有一个是刚刚寄信的，一个，
因为这课有确诊，所以我想看。
有确诊？
有2个确诊。
我没有在看。
对，就政大还算相对还算好，台大昨天就10几个人确诊，
而且宿舍都爆，
他宿舍整个爆，对，台大宿舍全爆，宿舍那个环境一定会爆，4个人一间，几个人一间那种，然后洗澡都还是都挤在大对啊。
这场6是6人确诊，而且这场6是最新
真的赶快买防疫器。你说，同学你说喽。笑死。如果是业务，就在校门口摆赚爆，然后多收100块这样。9块多会贷款，100。对啊。
Okay, so let's continue our class. So let me briefly introduce the homework 2. Also, data practice. And the question also, some of question might kind of like help you to write your term paper. And some is practice this data. For example, the question 1 is your research question. So far I think many of you can confirm what kind of research question you want to explore for your term paper. So this first question is just what's your research question, and second question is what's your treatment variable and what's your outcome variable. So you just write down and briefly introduce your research question. And that's something you can also write in your term paper. And also use the potential outcome framework to design or define the causal effect you want to estimate. So let's use the y1, y0, this type of thing to define the causal effect you try to estimate. And one thing you need to pay attention is sometimes the causal effect is not for whole population. Maybe you just want to estimate the causal effect for specific state or a specific subgroup. So that's something, so not just write down y1 minus y0, you might adjust this framework to your own questions, okay? And then is create sample for analysis. That's just let you practice 3 important commands. And I also send out the video for these 3 commands: the collapse, append, and merge. And these 3 commands will generate a new data set. So change your original data to some new data. For example, collapse is generate an aggregate level data set from the individual level data set. So you just practice, you generate based on your original data, and you create a new data set using the collapse, which is useful for your analysis. Okay. So, but maybe your analysis will not use such data set. That's fine. You can just generate whatever you want. And briefly describe this new data set. For example, this is the what kind level, the aggregate at state level, state year data set from the individual level data set. Something like this. And append is also another command that can combine more information, and it's vertical combine 2 data sets. For example, if you have the data set for 2000 and you want to combine 2001, 2002, you can use append to combine them together, and that will generate a new data set. And you also just practice this command and briefly introduce what's this new data set. For example, original you only have 2000 data set. And now you append to the 2001, 2002, so you generate this new data. You just describe. And merge is another command, also add information, more information, but it's horizontal combination, integration. It's sometimes maybe your data does not have some specific variable, and these variables are from other data set, and you can use merge to combine these 2 data sets and add more variable. So this also asks you to practice this command, and potentially it could be also useful for your term paper or your analysis. And you also need to describe them. Okay. And third part is visualize data and using histogram and graph 2 ways. So histogram is for only one variable. You just draw the distribution of that variable. So you can draw the distribution for your outcome variable or treatment variable. So something is you might also put that kind of graph in your term paper. That's something you can also do here. And graph 2 way is display the relationship of the 2 variables. So you can also use that kind of graph, maybe also useful for your term paper. And you can watch my video I just sent you for the graph. We will introduce the histogram and graph 2 ways. So you just apply something you learned in that video, this video to this homework. And finally, you will have preliminary analysis, and this can help you to do some preliminary analysis for your term paper. So, for example, the first question is regress, using the regression. You just put the regression, the outcome, and the treatment variable, and run this, try to understand the correlation of these 2. Is the answer for this question. But these should have some omit variable bias, and you can discuss here using the omit variable bias formula. you just learned in this class. And finally, you will include some covariates, and you need to discuss whether these covariates are back control or not. Okay. So this question is also try to accelerate the speed of your term paper's progress. Try to let you start to do some preliminary analysis for your term paper. But at this moment, you don't necessarily need to use some causal method. Try to estimate causal effect. Just do some correlation analysis. Okay. So any questions for this? Okay. So that's for the homework 2. Okay. So next, we introduce the sixth identification strategy you learned in this class, so-called the regression discontinuity design. And we know so far a major problem of estimating the causal effect of the treatment is the threat of selection bias. So all the course we try to eliminate the selection bias, because the selection bias will confound with the causal effect we try to get. Okay, and in many situations, due to the people who can select into the treatment, so we will make the treatment group and control group layout will be very different due to this selection issue. So the best deal with this problem is conduct the RCT, the randomized control trial. So you also learned in the beginning of the class. So in the RCT, why the researcher can eliminate selection bias is because we can control who can get a treatment and who cannot get a treatment. And a treatment assignment process is random. So due to this, we can make sure who get a treatment and who do not get a treatment, their characteristic will be very similar. So in that case, we can make sure treatment group and control group are comparable. The only difference between these two groups are one get a treatment, one do not get a treatment. And then we can attribute any change in the outcome to the treatment assignment, due to treatment group receive a treatment and control group does not. Okay. But conducting RCT is very expensive in the social science and also have some ethical issue, because you cannot enforce someone to accept the treatment which they are not interested in or they don't want to get. So that's why we learn several methods to deal with when we cannot conduct RCT. And RD is another method we can help her to get a credible causal effect if we cannot implement the randomized control trial. So instead of controlling the treatment assignment process, if the researcher have some institutional knowledge, some detailed institutional knowledge of why someone get a treatment and why some people does not get a treatment, we have knowledge know what's the key for the treatment assignment process. Maybe we can use this information to create the randomized experiment to get a causal effect, at least for these people. And that's the idea for this regression discontinuity design. The regression discontinuity design explores the fact that in our daily life, some rules can generate a discontinuity in treatment assignment. So some rule will make some people, if their variable pass some cutoff, they will automatically get a treatment. And some people, their such variable is below some cutoff, they cannot get a treatment. For example, there's some score, a test score cutoff for NCCU admission. So if you pass this cutoff, you get admission to the NCCU. If not, you go to another school. And you can use this institutional background, the institutional information, to compare those who just above NCCU cutoff, those just below NCCU cutoff, to compare their outcome, like their salary in the future, to get the causal effect of entering NCCU on your career. Because since those who have the test score just above or below the cutoff, these two group of people should be very similar. And some people may just lucky answer the right questions, so enter the NCCU. Some people just unlock to go to another school. And then you can safely to get the causal effect. So some treatment assignment is determined based on the threshold on some variable, like test score, like just I say. And this variable sometimes we call assignment variable, because this variable can, whether they above cutoff or below cutoff, can determine who get a treatment, who cannot get a treatment. So it's called, sometimes we call these variables assignment variable or rounding variable or forcing variable. And if no other factor does not change abruptly around the cutoff, then we can attribute to any change in outcome of interest to be the cause, the treatment. Okay. So if such thing happen, we can use regression discontinuity design. Okay. And here I give you one motivating example. One question health economists might want to ask, or public health or scientists may want to ask is, do healthcare service make people healthier? So that's very important causal question for the health economist. And sounds like this is not really important. Very obvious question, because healthcare services are valuable. The answer seems likely to be yes. That's why we need to provide a healthcare service. But if you simply compare the health status for those who receive more healthcare service with the health status of those who receive less healthcare service, basically you will get those who receive more healthcare service, their health status is not good. But does this mean more healthcare service make people sicker? It's not necessary, because we might confound with the causal effect of health intervention on health status and the selection bias. That is the correlation between the fact that sick people tend to receive more healthcare service. It's because they are sick, that's why they receive more healthcare service. And typically, the selection bias will overwrite the causal effect in such case, because in the data set, you usually will find the health status of those who receive more healthcare service, they tend to be sicker. And this could be the selection bias rather than the causal effect of healthcare service. So we need to eliminate this selection bias to recover the causal effect for these important questions. So a great way to answer these important questions is implement and randomize experiments. So instead of letting people to make their own healthcare decision, now we just flip a coin. If you get a hand, you can receive the healthcare. If not, you cannot. And that's great idea, but no one will allow me to do that, because healthcare decision is very important. It cannot allow just randomly decide. You must need to let the sicker people to get a healthcare service. So in the reality, we cannot really implement such randomized control trial. But we also face a threat of the selection bias when we estimate this causal effect. So how can we answer that? 3 economists, they design for a use the regression discontinuity design to answer such questions. They want to estimate the effect of health intervention in early childhood when they are just born on their later life outcomes. So this is very important, especially for early childhood. The baby tend to be sicker. So it's especially they might need the healthcare intervention. Okay. But obvious there's selection bias, as I just mentioned. The children who need more health care service in early childhood, they tend to be very sick. And these people, they will just have the worse later life outcome. For example, they have low educational attachment or other things. They tend to die earlier. So if we just simply compare the children who stay in the hospital for longer days compared with the people who does not stay in the hospital, you will always find those who receive more healthcare intervention, they tend to be sicker. But this does not mean health intervention is useless. So how does these three people to solve this problem using the regression discontinuity design? They use the knowledge, they know the doctor, they actually have the habit or maybe some guideline for the doctor. They need to pay attention to the children, to the infants with the birth weight just below 15,000 grams. If their birth weight is below this number, 15,000 grams. 15,000, no. 1,500 grams, sorry. 1,500 grams is considered a low birth weight. And the doctor will put a lot of healthcare resource on these people. That's the kind of guideline or some culture that the doctor will, in practice, the doctor will do that. And so this baby will be eligible for additional health care. And if your baby's birth weight just above this 1,500 grams, for example, 1,501 grams, compared with 1,499 grams, the doctor will put a lot of health care for these people, rather than those just below this threshold. But actually, these two groups of baby, actually their health status are all very dangerous. But one just receives more health care, one does not, due to this cultural issue or due to this guideline. Then we can just compare some outcome, for example, mortalities or some academic achievement between these two groups of infants, just below and just above the cutoff of 1,500 grams. And we might get the causal effect of the additional health care on the outcome they are interested in. Okay, so that's the idea of this paper. And this is their result. So for the RD design, you can, it's very important you show your result using the graph. And actually the graph can tell you a lot of, basically their result, a lot of things. So first things is, we want to know whether those who just below the cutoff really receive more healthcare service. And for example, this is the so you can consider this is kind of like treatment. So this is the days in hospital. So you can find the doctor really pay attention or put more resources for those who, the infant with the birth weight below the cutoff. And you can find, on average, for those who below the cutoff, they will stay in the hospital for 32 days. And if you are unlucky, just have 1 more grams, your average days in the hospital will drop to the 26. So it's kind of like 6 days difference. So this 6 days difference actually will generate very big change for their later life or their health status actually when they find. But maybe they also other healthcare service, healthcare intervention also change around this cutoff. So this just give the example. And they find they actually will, this intervention actually reduce the mortality. So for those who just below the cutoff, the mortality rate will reduce to around 10%. But this is still very large number. That means 1 of 10 baby, if your birth weight below 1,500, is 10% of them will be die. But this number is actually lower than those who just above. So for those who just above, they does not eligible for this additional healthcare service or stay in the hospital longer days. Their mortality rate jump to the 15%. So this is around 15% increase in the mortality rate. So you can consider this intervention actually reduce the mortality rate a lot, okay, from 15 to 10 by 5 percentage points. So it's around 15% reduction. And more interestingly is they also have some positive impact on their human capital. Their math scores at the 8th grade, is 14 years old. Those who receive more healthcare service actually when they are in the early childhood, their math score are higher than those who receive less. Okay, so it's quite striking result. This suggests the health intervention in the early childhood have very high return. It can improve the health status and also might increase the human capital. So this actually gives very straightforward evidence suggests, for example, the health insurance maybe should cover all the expense for this type of the children, for this type of infants, to make sure they can receive enough the healthcare service. Okay. So any questions for this? Okay. So also the RD design also can apply to the political science. This paper, they try to understand one important question in political science is, does political incumbency really provide electoral advantage? That means whether people for example, existing president, if they want to run the next election, do they have high probability to win next time? Because they have incumbency advantage. For example, they can use their administrative resources, try to help to do some election campaign. Okay, but there are some selection bias you need to overcome, because people who can win the election last time is because they are popular. So these people, they should be more like, they usually will compare with those who lose the election last time. They are more likely to win next time. That's just due to they are more popular, rather than because they are incumbents, they are in a position. Okay, so this author tried to use RD design, try to solve this selection bias. And how can he do that? Is they use the close election. That is, they compare the candidate who just barely won, just win very marginally, just 51%. And so barely become an incumbent. And compare with those who the candidate who barely lost, that is, they won't just have 49% votes, and they lose the election the last time. And compare these two people, these two candidates, two type candidate, the winning probability of next election. And since they are similar, have very similar vote share, voting, they should be all very popular. But just one candidate, they due to some random shock, they win. And these people, they just unlucky, they lose. And one become incumbents, and one do not. And we can use these comparison to get the advantage of becoming the incumbency advantage. We can use this by eliminate selection bias. And this is their result. They actually find, so this the assignment variable is the vote share last time, the previous election, and the outcome is the vote share, the probability of winning election next time. And 0 you can consider is 50%, below and above. And these two group of people, one get 51%, one get 49%. They should be similar, have very similar vote share before. But actually, the winning probability next time is become very different. And this difference can represent the advantage of incumbency. And this could be due to they use their resources, try to win the next time. Okay. So these also give the very obvious result for these very important questions. And the regression discontinuity design, there are a lot of discontinuity you can explore, either using the knowledge or some culture, or this is also very smart. They use this closed election to generate. And sometimes you can use the geographic discontinuity to get this, to use the RD design. So for example, this paper, they try to understand the effect of the unemployment benefit on the duration of unemployment. So that's a very important question, because people want to know, the government might want to know, if we provide more generous unemployment benefit, maybe people might reduce their labor supply. They don't want to try to find a new job because they can get the money for free. So they will stay in the unemployment status for a long time. So if that, the government might not really help them, might just make them stay in the unemployment status too long, for a long time. And this paper, they try to understand this causal effect. They use the fact that in Austria, some area, their unemployment benefits is extend to 30 weeks to 209 weeks. And some area still keep 30 weeks. And they can compare the unemployment durations in some area very close to the border. Two areas, they share the same labor markets, but one can receive 209 weeks, one area cannot, just 30 weeks, to conduct this design. So how do they do? Exactly is this. The shaded area is the area, the people, if they live in that area, they can receive 209 weeks unemployment benefit. And the white area is just 30 weeks. And the author does not compare the average unemployment duration for blue area and white area, because these two labor market maybe is not comparable. So the things they really compare with the around the county or region around the border. So they compare the people who just in the blue area and the people who just in the white area. And since these two group of people, they live very closely, they might have very similar labor market feature. And the only difference is these people receive 209 weeks unemployment benefit, and these people just 30. And they can compare these two people's outcome. So their assignment variable here is the distance to the border. Okay, so this is their result. They find, so the assignment variable is the distance to a border. So 0 is in the border, and positive number means they are in the blue area, and negative number is in the white area. And you can find, for those who just live around the border but live in the blue area, their unemployment duration is larger than those who live in the white area, but they also close to the border. And the change is around from 13 weeks to 26 weeks. So compared with their treatment, actually it does not change a lot, just change 13 weeks. But these people receive much larger, more than 170 weeks more unemployment benefits. But it suggests if you receive more benefit, you will stay in the unemployment status for a longer time. And they use this geographical discontinuity at the border to implement their RD design. Okay. So any questions for this?
Taiwan a member of ASEAN?
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 No. 东协
So could you use this to sort of compare the effects of joining the trade market on the economic growth or something? Like, so you have
compare the border?
So you have Taiwan's an island, it doesn't have.
Yeah. We don't have,
So compare that, it's China a member?
China is a member.
Yeah. So
You mean the trade union for the East Asia? Yeah.
Like, could you use it to
China is in that.
the effect on the two economies of joining? So joining the economy would be a benefit, and so because
That's interesting design. Possible. For example, maybe Thailand is not in. Thailand should be, but Cambodia maybe not. But you can compare the border. Yeah, but I'm not sure whether economic activity around the border is very active or not. Is it possible? No, only just forest there. Yeah, but it's interesting. Something you can do. Possible. Yeah. For example, trade war is one possibility. I heard some news. A lot of, because the China need to have very high tariff after the trade war. So a lot of Chinese firms just move to the Vietnam, cross the border. So maybe around the border, the economic activity have very different change after the trade war. Yeah, that's something. So any other questions? Okay. Yeah, so RD design the first RD paper is published in 1960, and in the education journal, is a Journal of Education Psychology. It's trying to understand the effect of the scholarship on their career, on their salary or later life outcomes. And why there's the RD here is the GPA. The whether you can eligible for the scholarship, you need to pass some threshold of the GPA, 3.5 for example. So they use this idea to estimate the causal effect of the scholarship on the some outcomes. And it's published very early, but for a long time, I don't know why, but social scientists does not really use this method until recently, until like early 2000. And why such thing happen is one possibility is very big data are available now, because the RD design need a very large sample size, since you only compare the people who just around the cutoff. Sorry? Okay. Yeah. The compare the same, you just use the sample around the cutoff. So even you have other individual in other for example like 1,400, actually you does not really use these people, because the thing why RD works is you compare the people who around cutoff, they are very similar. So the sample size, even you have like 1 million, but eventually you just maybe use these people who just their birth weight just around 1,500, or maybe just 2,000. So usually you need use the population data set to implement this RD design. And such big data set are available maybe after 2000, like within this 20 years. Okay. And also cutoff rule are very widespread. If you can just pay attention, you will find such cutoff rule might happen a lot. Okay. So there are two types RD design, and I will introduce this sharp RD first. And for the fuzzy RD, you will learn when we discuss the instrumental variable. And sharp RD is more straightforward. So the difference between a sharp RD and fuzzy RD is just the enforcement of the treatment. So for the sharp RD, nobody below the cutoff will get a treatment, and everyone above the cutoff will get it. So that means the treatment probability around the cutoff is changed from 0 to 1. So everyone above cutoff will get the treatment, and everyone below the cutoff will not get a treatment. That's the sharp RD. So you can consider everyone are complier, they follow the rule, cutoff rule. And fuzzy RD does not require this case. So the sharp RD is the fuzzy RD special case. So sharp RD just require, the fuzzy RD just require the probability of getting treatment has some discontinuity, has changed. But it's not necessary from 0 to 1. So that means the people who just above the cutoff, the probability of getting treatment is higher than those who just below. They just require this. So the sharp RD is the fuzzy RD's special case. Okay. And then when we learn the instrumental variable, you will learn you can use the cutoff, whether the people's assignment variable above cutoff or below cutoff, as the instrumental variable for the treatment. And that we will discuss when we discuss the instrumental variable. Okay, so next we use the potential outcome framework to let you know what kind of causal effect you will get if you use regression discontinuity design. Okay, and we use this paper to go through the key concept of the sharp RD design. And this paper is trying to estimate the causal effect of legal access to the alcohol mortality. So that is whether if you can drink alcohol legally, maybe may make you die. Okay, because you drink alcohol and then maybe drive the car and die, something like this. So they use this as example we use this example to go through the key concept of sharp RD. So here the treatment. So maybe you can have the break.对，但自己不显著，所以其实是没有影响。对，但它工时减少，可是薪资一样。你那个是总月薪，对不对？但你可能还要除一下 CPI， 去算成实质薪资，因为那个是年末，可能其实就会一直成长。就是2020一定还是会比2018高，可是可能你考虑通膨之后，它其实是下降的。对，你要去找一下每年的 CPI， 应该找得到，这个就一般都会有。
这个小机子
没有做。对，不是。
跟他小时候有点不一样，他小时候这样做家里非常的
所以你用
然后这几件事，然后这里考成两
是我在小时候，然后所以其实是超大的，对他做的事情，
对，没错，对，就是要有，对，所以不太能够防控的人，公司所以0.2
吃咖啡房间，然后花上多
小时，对，1周少0.44个小时。你可以。对，你就不是你这不是反过来， 你这边要放的 outcome， 所以是2或者是 hour one， 那你这边要放的是你要切成什么 group， 所以你这边是实验组每一年跟对照组，然后如果你之前不知道，但反正你这边其实放的是 WH， 那你这边放这样的话，对。然后直接往这边，你不要，你这边 EITC 的部分有一些你可以不用管它，对，但是你这边就要改，你就要改成那个，你这边写的 outcome。因为你这边前面这边产出来的就已经有可能是这样。没问题，对，这篇你应该是，对，然后你会有应该有2个图，一个图是给2，一个图是给2。那你这边，因为我在课堂上那个例子其实是自己在弄的一个东西，所以你这边其实应该是要加个 if， 它是实验组，跟 if 它是对照组。if 它是 WHL 等于 因为你要画2条线，一条线是实验组，一条线对照，然后你要一起去画。在没有在最后这个之前，对，加一个 WFHL 等于可能是2或者是 hour。这边你不可以放这个，这边你要放你自己写的字就好了。
我想要写的字。
对，就是这样，里面刮胡里面放，然后你比如说工时就是 hour， 对，这不是放变数，对，这不是要放变数。
我以为它是要放。
没有，但是你可以看我新放的图片。
好。
要啊，我这边要放控制的，你这边是概念是你对，概念它是一组画一条。
然后再同样一个是公式。
对。然后你那个 DID 那边你其实还可以再多放一些控制点，
就是好像
年龄啊，还有性别啊，这些不要 stack 好就可以，就是多少有多少个小时吗？
就他的回答。
然后多少控制这些东西。
就高什么？
应该就是这样。不用啊，就是没有，这边的 DID 我们多控制这些，
然后他应该叫老师也这样解释，就是告诉他们这样子。我们都没有说你来跟我拿这个字是什么来做那个写作的，不，是在这之前太了解，
是在大家会的都是热水厂，那他会想要让他帮我们
对，我这样附近你会吗？因为 它可能会操控它会不会超过15年，除非你超不超过15年是一个非自愿的意思。
如果他，
但有可能他没办法控制它会不会超过15年。但 RD 待会会讲有一个蛮重要的假设，可能会被违反，就是如果你可以自己很自由的操控你要不要超过好的。如果发生这样的状况，你就选败了，因为一定是比较想拿到的，机会超过。那它的概念就是有没有办法超过，有点像是无法控制的。但是你这是有趣的想法，可是你的资料上，譬如说人力运用调查，它的年就是15年、14年。没有很细，你没办法比15年多1个礼拜，14年少1个礼拜，这个可能还真的他没办法控制。但你15年对14年，这两种因为一个就是多1年，一个少1年。可是我觉得你可以做一个字 ，base difference， 它就不用要求一定要在很接近，就是可以15年以上15年以下一条，然后比较在这个叫对，就是就是一次金，这样子就会是
这个相对比较少，念到年纪你知道
对，
就是这个是给我的打击，是大家会为了要领
对，15年之后它就会有年金的选项，所以等于是看年金选项对于treatment group 的老伴的决定来影响。对，可是我好像我没有很确定会有什么影响。
因为我们刚刚原本是想说，就是大家发现，就是因为这是活越久的领越久，是大家会会影响到让大家有一个提前退休的。
哦，对，所以预期应该会是有年金选项会提前退休，会减少他的一个损害。
对，跟提前退休我
特别是满足的。
可是提前退休会想到这个是6很难讲，就是他知道他之后会他多年进选项之后，他知道他之后另外也可以领很多，所以他也会延后他的退休年。因为他知道原本他觉得是
不过这个也要想一下，就是说你觉得理论预期或是可能会是什么？对，因为这个你最后有一个结果出来，还是要有办法解释到底发生了什么事。
最常见还是用，就是你刚才讲用这个。
我觉得用 DID 应该比较理解。至少我可以分享给大家。我才知道处理效果是什么。我忘记了。我举一个生动例子。要举一个生动。Okay, so let's continue. So first we define the treatment. And in RD, the sharp RD, the treatment is fully determined by the assignment variable. So that is, assignment variable is we usually call X. And the cutoff for the treatment assignment is C. And the treatment variable we again call D. So if someone receives the treatment, D equal to 1, and if not, D is equal to 0. But the treatment here is determined by whether the assignment variable is above cutoff or not. So if assignment variable is above cutoff, this individual will get a treatment. And if not, they will not get a treatment. So in this example, we use this legal access to alcohol is in US they have the legal age for drinking alcohol. So if your birthday after the 21st year old, you can drink alcohol legally, and if not, you cannot. So it's for legal access or not, before and after the 21st birthday. So here the assignment variable is age. So whether your age is before or after the 21st birthday, and the cutoff is 21st birthday. And if you are above 21st birthday, you can drink alcohol legally. You get a treatment. And if not, you do not. You cannot drink alcohol legally. And potential outcome in this case, again, is also called Y1. So Y1 means the potential outcome if the individual received the treatment. So in this case is potential mortality rate if this individual can drink alcohol legally. So what kind of mortality rate might happen? And Y0 is the potential outcome if this individual does not receive the treatment. So let's call Y0. And you can, in this example, is the potential mortality rate if they cannot drink alcohol legally. And only one potential outcome can be observed. So observed outcome, we also again use the Y, and it's either Y1 will be realized or Y0 will be realized. But here, whether the Y1 be realized or Y0 be realized, it depends on whether their assignment variable is above cutoff or below cutoff. If their age is above 21st years old, the potential outcome, if they can drink alcohol legally, will be realized. And if not, Y0 will be realized. Okay, so that's the observed outcome. So ideally, for each individual, if we can observe two potential outcomes at the same time, we can estimate the average treatment effect. So that's what we discussed in the beginning of the semester. We can get the average treatment effect by just comparing the same group of people at the same time if they get a treatment or not get a treatment. These two potential outcomes. But it's impossible to observe these two potential outcomes. We only observe either Y1 or Y0. So we need to use some observed outcome, try to replace unobserved counterfactual. So in the RD design, it suggests we can look at the behavior of outcome around the cutoff. That can give us the causal effect. So the RD estimate basically is compare the observed outcome for those who just above. So it's the assignment variable is equal to cutoff plus some epsilon, and epsilon is close to the 0. So that means the assignment variable just above the cutoff, the outcome, with the assignment variable, the people, they have the assignment variable just below the cutoff, their outcome. And compare these two group of people, their outcomes difference. Later we will show that under certain assumption, it can help us to identify the average treatment effect at cutoff. So we do not use RD to identify the causal effect for whole population. We can only precisely identify the causal effect for the people who around the cutoff. So in the alcohol example is we can compare the people who just above 21st years old, their mortality rate, with the people's mortality rate for those who are just below 21st years old. And these can help us to get the causal effect of legally get access to alcohol on the mortality for those who are around 21st years old. So that means these causal effect, the causal effect we get from this RD estimate cannot really extrapolate to the 60 years old. And based on their finding, actually, it's also reasonable because they find those who, why the legally access to alcohol will make people die is because they drink alcohol and then have car accidents. And that kind of mechanism might not happen for those who are 60 years old, for those who are old people. So these causal effects you need to keep in mind is RD estimate can give you very good, very credible causal effect, but the causal effect might just apply to some subpopulation, and the population, that means the population, the group around the cutoff. But sometimes these people, this group of people, maybe is the policy trying to target. For example, in our case, young people maybe is interesting. You want to look at how does the legally access to alcohol on the young people rather than old people. Yeah. So sometimes the causal effect you get maybe is interesting, but sometimes maybe these RD estimate give you not very interesting causal effect. That's something you need to keep in mind. Okay. And so later we want to prove we can use this observed estimate, the RD estimate, observed outcome, to recover this every treatment effect at cutoff, which is unobserved, because we only can observe either Y1 or Y0. And under some assumption, we can claim this is equal to this. Okay. So one first assumption is deterministic assumption. This just say whether you get a treatment or not is fully determined by whether your assignment variable is above cutoff or not. So one is the indicator variable, means this statement is true, is 1, and otherwise it's 0. Okay. So in our case, an individual, if their age is about 21st years old, they for sure, based on the law, they can get legally access to alcohol. And if their age is below 21st years old, they cannot legally drink alcohol. So that means the probability of getting a treatment at cutoff, if you are 21st years old, is 100%. You can legally drink alcohol. And if you just above, just younger than 21st years old, just 1 day younger, you cannot by this law. So it's 0. The probability of getting treatment is 0. Okay. And another assumption called the continuity assumption. That's very important assumption in RD design. And this just say the potential outcome, their value are continuous at cutoff, close the cutoff. So that means the value of potential outcome does not have any discontinuity at cutoff. And this assumption actually implies except the treatment assignment are different. All other unobserved determinants of the outcome are continuous across cutoff. Only treatment assignment are different. That means the only difference between those who just above or those who just below the cutoff are due to their treatment status. Other are continuous. Other are does not have any discontinuity. And why? So this assumption assume that. So why I use this graph try to show that. So if this assumption holds, we can say any observed discontinuity in outcome can be attributed to the treatment assignment, because this assumption implies all other confounding factors go smoothly around the cutoff. Okay.
It's possible to check. It's possible.
Yeah. For unobserved things you cannot, but for observed things you can check whether other observed characteristics have any discontinuity around cutoff.
When you say all other unobserved,
Yeah, all other observed and unobserved, all. But for unobserved, we never be able to check. Yeah. Thanks.
we have to check observed outcome.
Yeah. Determinants. Yeah. So later we will have example to show we should check in the beginning. Yeah. So all the factor does not change or go smoothly around the cutoff. So why this imply this? So basically, these assumptions suggest Y1 is continuous across cutoff. So the solid line means you can observe. Dashed line means you cannot observe. And cutoff is here. So Y1 and Y0. So if you can observe Y1 over cross the cutoff, we suppose the Y1 looks like this. So that means the Y1 is continuous over across the cutoff, and Y0 also. And why this is implied other things does not change is because Y1, you can consider Y1 is determined by some function Z. Z is all the factors. But this factor does not include the treatment, because we already fixed the treatment. We just observe the potential outcome if they get a treatment. So the Y1's change does not, if Y1 has any difference, it's not related to their treatment status, because this potential outcome, we already just focus on the people if they get a treatment. What if they get a treatment? What will happen? So before and after the cutoff, they all get a treatment. So if this cutoff, this Y1 does not change at cutoff, that means all other factor does not change. So Y0 also. Okay. So if our observed outcome is this. Observed outcome. If we find observed outcome has discontinuity, based on this assumption, the Y1 and Y0 are continuous. This must due to the treatment contribute this, because after the cutoff, Y1 realized. Before the cutoff, Y0 realized. So this due to the treatment. Rather than this situation, rather than potential outcome has discontinuity at cutoff, like Y1. The people who stay in after the cutoff, their Y1 just very different from their potential outcome with treatment, just very different from those who below the cutoff. But this difference, the discontinuity in Y1, is not related to the treatment status, because we all focus on the people who get a treatment, if they get a treatment. So this discontinuity is due to other factors. And our assumptions say we don't allow this case. We assume they are continuous across the cutoff. So if we observe any discontinuity around the cutoff, it's not due to the other factors that determine the outcome. It's just due to the one get a treatment after the cutoff, one do not get treatment before the cutoff. Okay. So based on this assumption, we can attribute our difference in outcome to the the change in the treatment status. Okay. So any questions for this? But this is the assumption. But we can verify. At least we can verify observed whether observed characteristic has any discontinuity here. Okay.
Not fully for sure, because there's always something.
Yeah. Unobserved, we almost cannot sure. But for this RD design, because we compare the people who are very close to the cutoff, it's highly possible they are be very similar in terms of all factors in terms of the unobserved things. Yeah. Okay. So any questions? Okay. So the thing we want to get is the average treatment effect at cutoff, y1 minus y0 at cutoff, the average difference between these two potential outcomes. But for those who at cutoff, we can only observe y1, but we don't observe y0, because at cutoff, at 21st years old, you can drink alcohol legally, but we never observe y0. And RD design suggests we can use people whose age just below 21st years old is observed outcome to replace this y0. Okay. So why we can do that is based on the previous assumption. The first is y0 at cutoff can be equal to the outcome, the potential outcome without treatment just below the cutoff. It's due to the continuity assumption. It's because it is epsilon goes to infinity, very small. It is because they are continuous, so this will equal to this. Okay. And then, since they just below the cutoff, by deterministic assumption, even you just below very little, you do not get a treatment. So y0 will be realized. So then it suggests we can use this observed outcome for those who just below the cutoff to replace this unobserved y0 at cutoff. Okay. And very similarly, we can also replace y1 using the people who just above the cutoff. Okay. So this suggests this average treatment effect at cutoff can replace by these two observed outcomes. The difference in these two observed outcomes. So that is the people's outcome who just above the cutoff and the people's outcome just below the cutoff. Compare their difference. That will give you the RD estimate. And this RD estimate, based on the continuity assumption and deterministic assumption, can help you to identify the causal effect for those who are around the cutoff. Okay. So under this assumption, we can identify this unobserved average treatment effect by using the RD estimates. Okay. So any questions for this? Okay. So now we know we can use RD to help us to identify some causal effect for some at least for some subpopulation. And the next question is how to estimate this discontinuity. So that next thing is estimation. And for estimation, there are two types strategy we can get the RD estimates. The first is so-called a parametric global method. That is, we use all available data or all available observations. And estimate the causal effect based on specific functional form for the outcome and assignment variable. So we need to assume some functional form. The outcome is some functional form of our assignment variable. For example, in our alcohol example, we need to assume some mortality is based on some function of the age. And why this is important for us to estimate the discontinuity, I use this example to demonstrate. So this y-axis is outcome, and horizon axis is our assignment variable. And we want the cutoff is here. And our goal is try to estimate the discontinuity around the cutoff. And in this example, you can find actually the data point suggests there is no discontinuity. But if you impose right functional form for the x and your outcome, for the assignment variable and your outcome, you might get the wrong discontinuity estimate. For example, if you just use linear function to estimate the assignment variable and outcomes relationship, you might get this result. You use a linear function and take their intercept, compare this intercept and this intercept, and you will get the discontinuity. It's very big. But actually, it's just due to the assignment variable and outcome, their functional form has something change around the cutoff due to this nonlinear relationship. So if you use, for example, second order or third order, maybe you will get no effect here. But if you use linear, you might get some discontinuity estimate. So that means the functional form assumption, use the right functional form between the outcome and assignment variable is very important for you to estimate the discontinuity at the cutoff. So in our designs, in RD designs, we usually will use the very flexible f of x, the functional form, to estimate the relationship between outcome and assignment variable. Okay. So in RD, basically we implied our potential outcome, if there's no treatment, is determined by alpha and this function, assignment variable function. And y1 is y0 plus rho. And rho is a treatment effect. It's a causal effect. So that's why we usually estimate this regression. So p equal to 1, you get a treatment. 0, no. Okay. So if you can get use the right functional form, the rho will represent the discontinuity estimate here. Okay. So usually we will impose the flexible functional form, p order polynomial, to estimate the x and y assignment variable and outcomes relationship. That's something. And our key is try to estimate this rho. And typical case is we usually will allow the assignment variable can be differ on both sides of the cutoff. That means assignment variable has different relationship between the outcome on the both sides before and after the cutoff. So usually we will include the x and interact the treatment variable with the x. Okay. So that means we will include not only x, but also treatment variable interact with the x. And this will allow different relationship before and after the treatment, before and after the cutoff. So for example, this means before the cutoff, below the cutoff, the x and outcomes relationship is beta 1. But after the cutoff, just above the cutoff, the relation is beta 1 plus beta 1 star, for example. We usually will allow very flexible relationship. Because it's possible maybe here is linear relationship and next will become a quadratic relationship. Okay. And also, in the practice, we will also recenter our assignment variable to cutoff value. And that's just for computation. It's easier for computation. So usually the assignment variable we put in our regression is x minus cutoff. So for example, in our alcohol example is age minus 21st years old. This. And this step will just ensure, because the causal effect we are interested in is at cutoff. And if we do that, that will help us to get the causal effect directly, just estimate the rho. And I will show you this. So typically we run this regression, the outcome and the treatment dummy, and we are interested in the rho, the causal effect. Let's measure the discontinuity at C. And x lambda times the treatment. So we allow they have different relationship. Then x lambda is x minus c. And why we usually do that is because we want to estimate the causal effect at x equal to c. So that means we want to estimate x equal to c. So in that case, this part will all become 0. If we focus on the treatment effect at cutoff. And the rho can directly represent this discontinuity. So if we do not recenter like this, you will directly use x. You will need to add a lot of c plus the rho to get a causal effect. So this is just for the computation issue. So typically we will do that. We will just recenter our assignment variable to the cutoff. So in alcohol example, we will estimate the following regression, and maybe we just assume the assignment variable and outcome, they have the cubic relationship. So like third polynomial order. So we run this regression. So we control the assignment variable minus the cutoff, and we also allowed the assignment variable and outcome, their relationship can be different before and after the cutoff. So we interact the treatment value, treatment dummy. Treatment dummy is above is 1, below is 0, for example. And the effect of legally access to alcohol on mortality at age 21 will captured by this rho. Okay. And this is their result. They focus on whether their age is above 21st years old or below 21st years old. And they first look at the deaths due to all cause. That means all the total number of the deaths. Okay. And they find is very significant. Like the death due to all cause is increased by 10 percentage points. I forgot the unit, but it's positively increased. And this is all due to the external cause. That is the cause due to like drive the car or other things. And for the internal cause, there's not significant. And internal cause could be the cancer, and that is not doesn't really make sense. If you just can drink alcohol legally just one day, it does not really make you die. And their graph also suggests that. So this is the deaths per 100,000 people. And their main result is this, and the assignment variable is 21. And you can see their discontinuity estimate here is there are some discontinuity. So that means if you can drink alcohol legally, that you really make you have high probability to die. And all of the discontinuity are driven by the external cause. So sudden after 21st years old, you die due to some external cause, like a car accident. And for internal cause, you don't find obvious discontinuity around the cutoff. Okay. So any questions for this? So these give you very straightforward evidence that just drinking alcohol might have some negative impact on the health due to this. But this estimate might only can apply to the young people rather than the very, very old people. Okay.
So what's the internal?
Internal, yeah, internal is here.
So
What kind of cause?
Yeah, I mean, how does occur come out? This is internal.
The cancer, like yeah.
I see. Just other factor that you can observe.
No, they have some definition for the external cause and internal cause. And to my understanding, external cause is just due to the accident, and internal is due to the disease. But it's hard to imagine why you just drink a little bit, just one day after the 21st years old, it can make you die due to some cancer, and it's induced by the alcohol. It takes long time to make you die. So this analysis, they cannot really apply to like such cause make you increase the mortality due to the alcohol.
My point is there are so many possible diseases, so many things you have to check, right? So the internal.
Oh, it's all the disease, all the they call internal cause.
So they do have a list of the variables. Right?
Yeah. For the public health, they or medical, they have the formal definition for external cause of diet up to death and the internal cause. But I just not really know. But to my understanding, is external cause is most are the accident or car or motorcycle, something like this.
So essentially, they're showing for this outcome of the variable, you did see the discontinuity.
Yeah.
For
That's
other type of outcome, you don't see this kind of continuity. That's the point they want.
Yeah, and they say this makes sense because their results you can consider is kind of like the short run impact of drinking alcohol. You just can legally drink alcohol just one day or 1 week. It cannot die due to some internal cause, due to some disease, cancer. It possible is just due to some behavior. You drink and drive the car and die.
So the question is, generally, when we apply RBD, what do we need to do something like that, or this is only specific to this case?
Oh, we need to draw the graph. That's for sure. But you mean you need to divide by several groups?
Yeah, or
yeah. It depends on the purpose. This is try to dig out the mechanism. Try to show that why you find that the increase in the mortality. But people might want to ask what's the cause. So they just further divide by these two types. Yeah. Okay. So any other questions? Yeah. So So in the parametric approach, the key issue is whether you use quadratic or cubic. What kind of functional form assumption you need to assume? How to pick up the functional form? That's the key issue, because it will affect the discontinuity you estimate here. So in the literature, there are two approaches, but I will only focus on the AIC approach because people seldom use this F-test approach. So but I still say something here you can read by yourself. So AIC approach is use some information criteria that you might learn in the statistics course. And the AIC is the criteria to help you to select the model. So what kind of covariates you need to include in your regression, you can use AIC to decide. And basically, it's describe the trade-off between the goodness of fit, your model fitting, and the simplicity of the model. So the goal of your regression model is you want to use the simplest model, try to get the best fit. And that can apply to RD to help us to select how many polynomial terms we need to include in our regression model. Okay. So the AIC is determined by these two components. The first component is a number of sample times log of the sigma square. So what is sigma square? This is just the residual variance. That is, when you control all the polynomial terms, you will get a residual, and the variance, you calculate their variation, the variance. And you can consider if you include more polynomial terms, like linear, quadratics, cubic, if we include more, the residual variance will become smaller because all the variation will be captured by if you include more covariates. So this term will be decreased if you include more covariates. But they also have penalty here, the P. P is the number of parameters you need to estimate. That is the coefficient here. So if you include more polynomial term, you need to estimate more coefficient. So the number of P will increase. Yeah, but they do not focus on this issue in these criteria. They just focus on these two trade-offs. Yeah. So if you include, for example, original model is you just use linear. If you include the second order polynomial term, it will have this trade-off. It will increase your number of parameters you need to estimate, but might reduce the residual variance. So the goal of it's not sure whether the AIC will become larger or smaller. So the goal is you choose the model with the smallest AIC value. So that means they kind of like try to balance these two. They can use the very small size of the model to feed the data well. So the principle is you can try several models that give you different AIC. For example, first you use the linear. You just assume X and Y is linear. Just put a linear term. And second, you put second order. And maybe you try third order. And you compare with these three models AIC. And pick the smallest one. That's the best model. You can justify, I want to use this model to control the functional form between the assignment variable and the outcome. Okay, so that's the typical case we will do when we do the RD. Okay, and the second approach to estimate the discontinuity is using the non-parametric or so-called local method. And that is, we just use the observations around the cutoff. And so what do we mean around the cutoff? We need to use some way to define where is the neighborhood around the cutoff. So that is, we just compare the outcome of the treatment and non-treated observation within specific interval. We call bandwidth. So this approach, the key issue is not choose the functional form of the assignment variable and outcome. Is the issue which how we define the neighborhood, how we define the bandwidth. Okay. And because the bandwidth actually has the two trade-off, and I will use this example to the following example to demonstrate this trade-off. And we have two ways to do that, to estimate the discontinuity. One is just compare the means of two groups of people, their mean difference within specific interval, specific bandwidth. And another is so-called local linear regression, and that's the non-parametric approach typically we'll use, and we will discuss how, if we use this local linear regression, that can improve the discontinuity estimate around the cutoff. So first, we just simply comparing the means in the two interval around the cutoff, and that generally will give you a biased discontinuity estimate. So here I just give you the example. The y-axis is the outcome, and horizontal axis is assignment variable. And here is a cutoff, and you can see there's no discontinuity in this example. No discontinuity at cutoff. And the non-parametric approach is doing the following things: is we just use within the specific bandwidth we call H. That is, we just say this is around the cutoff, and we just use the sample around below the cutoff and just above the cutoff. We just use this sample and calculate their mean. So for example, if you calculate the mean here, the average outcome is from here to here. So on average it could be 8, right? And for this part, the average outcome, if you use all the available data here, the average outcome could be B. So you will find the effect. You use this average difference to represent the cause of the discontinuity estimate here. And actually, this gives you some bias, because the discontinuity estimate you get is AB, very large. And this is because you does not use enough small bandwidth. If you have a lot of sample around the cutoff, you can further reduce the bandwidth. If you reduce the bandwidth, you will more close to the truth. Okay. But if you use smaller bandwidth, you face the trade-off. That is, you don't have enough sample size around the cutoff, and your estimate may be very unprecise, not very precise. So that's the trade-off for choosing the bandwidth. Try to balance the correct estimate for the discontinuity estimate and precise of your estimation. Okay. But using the non-parametrics literature, we can reduce this bias using the same bandwidth, but reduce the bias using the local linear regression. So that is, we simply estimate the linear regression within the this bandwidth, within this bandwidth. And the bandwidth, the regression is like this. again, the Simon variable and outcome. And the key is we want to know the intercept at cutoff. So if we run this regression, you basically run this regression. And using the same type, the same large bandwidth, and you run this regression. And you just focus on the estimate at the cutoff, the intercept. So here, this is the just below the cutoff, so it's alpha. So A plum is alpha, B plum is alpha plus rho. So this is rho. And this is not the same as the no discontinuity, but the bias is smaller compared if you just use this, or use the simple average. Okay, so local linear estimates will give you better estimate for the discontinuity estimate at cutoff, even you use the same bandwidth. So if you can further reduce your bandwidth, this estimate will more close to the estimate, the truth. So in the non-parametric approach, the question is how to choose the bandwidth. And the bandwidth choosing the bandwidth basically try to balance two things. One is the estimate bias, one is precision. So if you use the large bandwidth, you will have more data points, so you will get a precise estimate. But your estimate might be biased because your result might not very close to the truth. But if you use small bandwidth, you might get a better result, less bias, but maybe you don't have enough sample around cutoff, or maybe no sample around cutoff. So in that case, you cannot get any estimate. So the bandwidth choice is try to balance these two. Okay. So any questions for this? Okay. Okay. Okay, I just have one slide for this part. So how to choose the bandwidth? There are two ways. One is cross-validation approach. Oh, sorry. Okay, so in our example, we might use the bandwidth. You use some way to choose the bandwidth, maybe 180 days before and after 21st years old. And use this local linear regression to estimate, to get a discontinuity estimate rho. That's typical case we will do. And usually you will show your reader your estimate is quite stable, not very sensitive to your bandwidth choice. So you will run the regression discontinuity estimate for each value of bandwidth. So sometimes you use 0.3 years before and after 21st years old, 0.4 years before and after, and you get very stable estimate. And it's also acceptable if you get quite noise estimate if you use very small bandwidth because you don't have enough sample. So that's people doesn't really care if you estimate on very noise if you use very small sample in the very beginning of the bandwidth choice. But at least your result should be very stable after certain points of your bandwidth. Okay. And in the literature, we also have some way to help you to choose the optimal bandwidth. And you can also report, say, I trust my main result is based on the optimal bandwidth here. The optimal bandwidth is 1 year, 1.1 year, for example. And the optimal bandwidth, there are two ways to get. One is so-called a cross-validation approach. Is basically you choose the bandwidth, use a lot of choice of bandwidth, and each bandwidth you try to get the to choose the best fit for the relationship between the outcome and assignment variable. So you can base on the RMSPE or some predict error evaluation, and you choose the bandwidth that can give you the smallest predict error. That's one way you can do. That's the optimal bandwidth. Another is some econometrician or statistician, they derives some optimal bandwidth formula, because you can imagine the bandwidth, they have some trade-off. So based on this trade-off, you can formulate your optimization problem. And based on this problem, you will solve the problem and based on try to minimize the mean square error, and you will derive the formula. And the formula will say you need to plug in some parameter, and if after you plug in this parameter, you will get the value for the optimal bandwidth, for example 1 year or 2 years. And there are several algorithms can generate this optimal bandwidth, and they all have the theta and R package, so you can also use. So sometimes you can use this optimal bandwidth as your main result for your RD estimate. Okay. So I think that's all for today's class. In the next week, we will continue the RD design. I think, yeah, it's 7. Yeah. So any questions? Okay, if not, that's all for today's class.
或者是用 parametric，
对。
那 parametric 它你用 polynomial，那我的 question 是为什么你一开始要放进去那么多的 polynomial？ 如果没有放那么多 polynomial， 会造成问题是不是？
不会，没有，其实没有，一开始，因为我写的只是一个 general form， 其实是不用放那么多，其实通常放到可能3次方就算很多了，就是它其实没办法穷尽知道说，这到底是几阶的才最好啊。
就是因为你越多阶，它其实会让那个真正的服务的这个消失，会不会有问题？
不会，其实放，譬如说你直接放5阶，譬如说这样，譬如说这个，你放3阶，可是它的实际上是一个 linear term， 它就只是2阶项、3阶项接近0这样而已，它不会影响到它不会产生什么不好的影响。
这 polynomial 的东西理论上是会影响到那个 row。
不会。但是如果你放的太简略，没有 capture 到它的 non-linear term 的时候，它就会影响到你的估计。因为你会错误的以为它有 discontinuity， 可是它实际上是一个 non-linear 的 relationship。
所以你觉得那个 polynomial 到底它的意义在哪？它是类似一个 control。
对，它是一个 control。
以前类似那种以前我们常会那个 confound character 啊，或之类的。
对，比较像是这个，就是它是 confound 那个confound 你这个 discontinuity 估计。如果你没有放出正确的 term 的话，对，所以你其实是可以就一次放3、4个3次方或3次方或2次方这样子，因为大不了他们如果是 linear， 大不了它就是如果真实的方程是 linear， 大不了只是后面就消失不显著这样而已。但是如果它实际上是一个 quadratic 或者是3次方，你没放，而只放一个 linear， 就有可能出现这个问题。所以通常会是先把图先画出来，你可以看一下大概是它用 linear fit 比较好还是不要。
对，那这样开始好奇是你要分就是 parametric 跟 non-parametric， 那应该理论上要2种都显示出来给大家看。或者说有没有什么方式可以挑哪一个是比较可信？
一般的他会 如果你的样本够多，就是你在 cutoff 附近样本一大堆非常多的时候，
那你就直接用 bandwidth，
你就直接用 non-parametrics。大部分人其实会用 non-parametrics， 因为那个会有比较像 RD 的精神。因为 parametric 的做法有一点是靠那个 functional form 去 extrapolate 它在这个 cutoff 的形态。
太少了，然后
对
它需要用那个去。
对，但是如果你的样本数很少的时候，你就用 parametrics 是大家可以接受的。对。
I just have a question. For this example, do you have the data and the data resources or not? For this example?
Oh, for the alcohol example? Let me check. I guess they use some confidential data for the death record. I'm not sure in US whether their death record is publicly available or not. But in Taiwan, it's confidential.
Okay.
You need to go to the data center to handle this data set. But I remember if you Google, maybe you can find the death statistics or some anonymized death records produced by U.S. government. They might allow. I think they allow some data which is anonymized, is released for the research.
Do you have any other example for this one for the RDD but with the data so I can like be comparing?
Date RD. I don't.
Because I think it's more useful for me to take a look at doing that at the same time, like what they are doing, like using the data and the information that you're providing to us.
Oh, but I will give you the examples, data example, which you will have the data, and you can practice.
Okay.
So
in the next slide.
Yeah, next.
Okay.
But I can put in the website the link to add this. I haven't put the RD do file and data there, but I can put there, and you can download. Practice.
Okay. Thank you.
Yeah, no problem.
然后再问他关于 RD， 就是如果是像这种就是年纪的是比较可以使用 RD， 就比如说因为他107跟180年龄到61岁，然后就会比60跟61岁他们的。
没有，这边不是这样比。这边，但我有一个博士生在做这个题目，我们不是这样比，是他这个东西是比他这个出生年，这个其实会造成很大的 discontinuity。这个规则如果你仔细去看，它就是在说，如果你是在某一年出生啊，我不知道多少年，但反正它有 cut off， 可能在1947年，譬如说，如果你在1947年12月31号以前出生，
对，
你60岁就可以领退休金。但如果你是1948年1月1号生，
对，
你就要变到61岁。我们就是用这个 discontinuity 看这个对 labor market 的影响。那它是非常 sharp， 因为它只差一天出生，它就晚领一整年的退休金。对，然后这个会让他们，我们现在结果是看他退休年龄就晚了半年，然后他的请领时间就晚了0.8年之类的，对，之类的，对，这是可能，对，这是，但你不是你这边说的这样，我们不是这样做啊，我们是这样做，了解，对，我那边有劳保资料，所以如果以后有兴趣也可以用。
这样，所以这个
我的学生在做，
好，看看你，那我就专注在前面那个
年轻化的影响。你其实在问的是年轻化的影响，
对，
其实也很重要，这是蛮重要的问题。对，年轻化的影响。好。
我问个老师私人的小问题了。为什么会比较鸟巢？
鸟巢因为我头发 我头发如果长长蛮卷的，
哦，
所以高中就有这个外号，活动鸟巢。对。但你怎么知道我的外号？哦，蔡志远讲的吗？
蔡志远蔡老师透露说老师你很喜欢用 Nest 这个
对啊，因为
对，
呃。
然后我就然后说你。